Hey everyone, you're watching the latest edition of Astraveo's Coast to Coast podcast of science, astronomy, and the world around us. My name is Joseph, he's David, and we're just two friends who happen to be professional astronomers with a deep love of telescopes, astrophysics, and all things science. So we've got a great show for you today. We're going to be talking about CLOUD-9, a very exciting new discovery, a newly discovered starless gas cloud, very close to us, just 4 megaparsecs away, that might have big implications for our study of the universe. So, David, you want to kick us off?
Hello, good evening, Joseph. I love the fact you say 4 megaparsecs.
It is, right?
Yeah, it's on the grand scheme of things. It's
It's pretty close.
Yeah,
You
really.
know, it's a lot of zeros on the redshift.
Yeah, 0.001 or something. Yeah.
Exactly. I think it's even closer. I think it's at least 4 zeros, right?
Oh, really? Oh, yeah, I
Yeah.
don't know. Yeah.
23 IXF was, I think, 6 megaparsecs, and that was like 4 zeros.
Okay.
I think, yeah.
You're looking at that now, aren't you?
Exactly.
Anyway, we'll get going. Thank you for making
Yeah,
me laugh as always. Oh my gosh,
of course.
crying actually. Yes. Flash McQueen in the background. I just see.
It's such a great dream.
Oh, such a fun one, yeah. So, okay, so we're going to talk about CLOUD-9, which is a really cool object that has recently been discovered. It was first detected by a ginormous telescope. I think it's got the title of the biggest telescope on Earth.
Was it? Is it now? Because what about what Arecibo? Was Arecibo bigger, but then it broke?
No, I think this is. I think this is actually a. It's bigger than Arecibo, but yeah,
Oh well.
Arecibo is dead, unfortunately.
Okay.
It's from derelict now. But this is the FAST telescope, the so-called FAST telescope in Guizhou region in China. It's I think it's a couple of 100 miles north of directly north of Vietnam, so it's sort of southeast China. And it's wonderful. It's definitely ripe for a Bond film or something because this is nestled, as you can see, in a natural geological feature in the local valleys there. And this dish is 500 meters across, which is 5 American football fields or a really, really long golf hole.
What about bald eagles?
I don't guess there are any bald eagles that live there, but maybe.
I mean, how many bald eagles end to end is the
Oh my
for,
gosh. Well,
for
if a
freedom
bald,
for
yeah,
freedom eat it?
yeah, right. So if the wingspan of a bald eagle is about 2 or 3 meters, it's about 133 bald eagles.
Wow. Okay. Yeah, David had to study this for his citizenship exam.
Oh, okay, yeah, that's right. I became a U.S. citizen based on measuring telescopes with bald eagle wingspan.
That was his PhD thesis.
The great citizenship test, by the way.
That was, yeah.
How many bald eagles side to side could you put across the world's largest terrestrial telescope?
Sounds like a trivia night question.
I know it's brilliant. I actually love that.
I love it. I love it. But yeah, so it's very big. Can it move?
That's a great question. It cannot. It's actually fixed. You can see there are structural struts at the bottom four center of the image. No, this telescope is affixed to the mountainside essentially. Obviously, if there's an earthquake, it will move. But you can see that. Obviously, you can see there are several control towers, or they're called wire towers. But yeah, there's I can see 6 of them, I think, in the image. And what they do is they have a system of cables, and if you do remember the early Bond film, I think it was with a view to a kill, maybe. They did do a Bond film in Arecibo, which was the radio telescope in Puerto Rico. And those wires support what's called the cabin. And the cabin essentially is it is fairly big. You can actually walk inside it. It is that big. It's an enclosure where you put the radio telescope instruments, the sort of the receivers, the detection part of the system. And those receivers are suspended above the parabolic surface of the radio dish at one of the foci, and you can, with the cabling system, you can actually move. You can almost steer the telescope, even though the telescope itself is fixed into the mountainside. The instrumentation cabling of the cabin can move it around. And so, in fact, when that cabin moves around, you don't use all 500 meters of the dish. Effectively, you use about 300 meters of the dish because you get this sort of receiving aperture that wanders over the surface. And when I say wander, you can direct it. And that sort of allows the telescope to sort of point in different directions, even though the reflecting surface is itself stationary.
That's pretty amazing, and I think you can actually see the wires in this image going down to the cabin from each of
Oh,
the
yeah, there you
towers.
go. Good
Yeah,
idea. Good
that
spot.
is.
Yeah.
It's very faint, but I do see. I think I see all of them. That is pretty crazy, and it's kind of cool to have a telescope that the Earth really is what's pointing in. More so than usual, which is pretty
Oh
amazing.
yeah, no, it's incredible. Now
Yeah.
this is one of these problems. I think the South African Large Telescope, the SALT telescope, is similar in that you can't steer it per se, and then that one in South Africa, the the um, the declination axis is essentially fixed to the latitude, and again they move the tertiary mirror, or is it? Yeah, I think it's the tertiary, secondary, maybe the secondary. No, they move the secondary mirror so it effectively points, but you can't then point, say, to the southern hemisphere because you can't get that low down in the sky. So this telescope can't point in the traditional sense. So it has a somewhat limited range of view, but obviously, with it being fixed, you essentially wait for the sky to pass over you as the Earth rotates.
It's just crazy.
Yeah, amazing, amazing.
It's remarkable, and it's not the only big telescope that was involved with this discovery. So I have the
No,
VLA.
no, yeah, there's a couple of others. Now, just as I said, that was the Chinese
Yeah.
fast telescope is 500 meters across. The VLA is actually a network of 27 dishes, antennae, as we call them in radio astronomy, in a Y shape there. And I think the discovery configuration was in the D configuration, which means basically the antennas are spread out as they can be on that Y track. Each dish is 25 meters in aperture, which is about 6 or 7 maybe bald eagles across. Now, the reason
Like it's difficult to visualize how big that is. So this is for
Oh,
the video, which is
oh,
people
that's
for
okay.
scale. Yeah,
Notable.
yeah.
Oh, yeah. They are very, very big dishes.
It's so big. There's 28 of them. Like it's such a big
Oh,
telescope.
yeah, 27, I think. Yeah.
That's 27. Yeah, sorry.
Yeah. And if anyone's interested, these are the same radio telescopes that were used and featured in the film Contact with
Mhm.
Jodie Foster and Matthew McConaughey. And so really, really beautiful system. It's a real radio telescope observatory. And the reason why this one's particularly interested, if you can show the Y configuration again, yeah, the reason why they have lots of smaller dishes instead of one big dish is A, it's just very expensive to build a big dish. It's hard mechanically to support that much material over such a large area. But these dishes actually can move relative to each other. Not that far, and you can probably tell. I don't know the ultimate size of the array, but it's something like one, maybe a kilometer or something like that. But when you spread these dishes out over a large area, you effectively make a bigger telescope, and that increases the angular resolution. So you actually get a finer angular resolution while still collecting a lot of photons, radio photons in this case. And so it's actually lovely that you can do that. That you can really bump up the angular resolution, which is actually exactly what we do in the Event Horizon Telescope.
Yep.
For the work Joseph and I do in detecting the emission from the black hole at the center of our galaxy and the one at the center of the M87.
It's this exact same principle as this, but just taking it absurdity where instead of moving them a little bit along these tracks, you're moving them, but they're all the way on the other side of the world.
Oh yeah, well that's true. We have a lot longer baseline. Yeah, so our
Yeah.
our angular resolution is absolutely ginormous, of course. And also, it was sort of followed up upon. The discovery was followed up upon also by the Green Bay telescope. The VLA, by the way, is in New Mexico. It's about 100 kilometers southwest of Albuquerque. But it was also followed up on with the 100-meter dish, a single dish, in a Greenback telescope in West Virginia, which is, I think it's a couple of 100 kilometers south-southwest of Washington, D.C. So nestled up there in the what would be part the foothills of the Appalachians. And so those two telescopes did follow up its discovery.
So a lot of big telescopes getting pointed at this thing. So what I have a figure here sort of the 21 centimeter line. So can you tell us how these telescopes observe this and how it was used maybe to get into the discovery that we're going to talk about today, CLOUD-9?
Yeah, so this is super cool, and it's actually one of my favorite parts of astrophysics. In fact, is the 21 centimeter line is essentially a hyperfine transition of, as you might expect, all things fundamental in physics and astronomy, of hydrogen. And so you see a couple of interesting things here. The background image you're seeing is actually hydrogen gas emission in 21 centimeter line, which I'll explain in a second. All that orange stuff is hydrogen in the Milky Way. And so what you're seeing is that plane, that flat line, is basically the plane of the galaxy. excuse me, and then you see some emission away from the plane. But everything that's glowing in that image in orange or yellow, yellowy orange, is hydrogen. And so when you point a radio telescope to look at the wavelength of 21 centimeters, which is 1.42 gigahertz, so it's in the radio range, which is why we're using radio telescopes to detect and discover these objects. Oh, right there, it shows you, yeah, just below, I think a 1.424 gigahertz, I think it is. What you're really discovering is what is a hyperfine transition of hydrogen. And what's happening is, to a lot of hydrogen, you'll get one proton, one electron. Obviously, that's the first element. And as all baryons spin, and they tend to spin like this. And that's just one of the fundamentals of physics of these fundamental particles. Well, what can happen is this is a relatively high energy state. And so the system, the proton-electron system, can absorb energy from the sort of intergalactic soup. And when you have the spins aligned like this, like doing this, the electron and proton are both doing this, it is stable, but about once every 100 million years or so, the system will decide let's say the system, the electron proton, will de-excite. And what it does do is, what's wrong with that? If that's the proton, and this is the electron will flip its spin from up to down. And now the system is in a lower energy state. The electron orbiting the proton is very, very stable with spin opposite. And when that occurs, that's called a hyperfine transition. And to do so, it has to lose energy, right? Because this is a slightly higher energy state. When it does so, when that electron flips spin, it releases a photon of exactly 1.423 or 4, I can't remember the exact number, gigahertz, which corresponds in wavelength space to 21 centimeters. So what you're seeing here is, even though it only happens about once every 100 million years or so, all the hydrogen in the galaxy at some time is going to have this transition flip. And so what you're seeing here in the Milky Way image is some of the hydrogen has done this hyperfine transition, and it's emitting this 21 centimeter or 1.42 gigahertz radio frequency line. So we can detect the hydrogen in our own galaxy. And so, of course, most of the hydrogen is in the galactic plane, because, of course, that's where the vast majority of star formation occurs. And what are most stars made of? Mostly hydrogen. So it makes perfect sense.
Wow. So this transition occurs once every 100 million years, roughly, but there's so much hydrogen that it's happening all the time. That's pretty incredible.
That's exactly it. Yeah, it was first, I actually had to look this up. It was first theorized by a Dutch astronomer called Hendrik van der Hulst in 1949. And it was actually observed, 1944, I do apologize. And it was actually first observed in interstellar space in 1951.
Oh, wow. That's pretty recent.
Pretty recent. I mean, Dove radio telescopes are relatively recent, right? Essentially, they've only been around sort of just under 100 years. So this is all relatively new science.
There are sharks that are older than our entire concept of radio science.
Yeah. Well, there's that 400-year-old shark that's...
Yeah, the Greenland shark.
Yeah, it's incredible. Yeah. So that's a good way of putting it. Yeah.
Yeah. So, okay. So basically you're saying that this hyperfine transition is a really effective hydrogen detector. Then in this image, we're sort of using it to see the hydrogen in the Milky Way. But for the new discovery, we used it outside of the Milky Way galaxy and tried to look for hydrogen elsewhere. And so this is a paper from 2023 that is sort of the progenitor of this discovery. You're going to see more conversation in the news about this 2025 paper by Anand et al. But CLOUD-9 was originally discovered in this Zhu et al. Paper, where they used that big, fast radio telescope that we discussed earlier, and they made these hydrogen maps at the 21 centimeter transition, right? Yep, and they were looking at a galaxy that's pretty close to Earth, M94, and this galaxy is only about 13 million or so light years away. And they mapped out all the hydrogen that they saw, and they mapped out these regions, region 1 being the primary galaxy M94, but then there was also all these other sort of regions that they identified, and region number 9 was very unusual and became known as CLOUD-9. So can you maybe take us through what we're seeing with these maps, David, for our audience?
Yeah, the Zhu et al., their team, were quite literally on CLOUD-9. God. Hashtag astrophony.
Oh, what?
That's the end of the podcast.
Someone keep David away from the social media accounts.
Yeah. I just made that. I made that up on my own, by the way, just for the
Oh,
record.
whoa. You don't
Yeah,
say.
that was a dad joke. Just
Hashtag Astro funny from the
Bit of
mind that
Astro
brought you Astro Papa.
Astro Papa, Astro Funny, Astro.
Yeah.
Oh my god. Yeah, so this team Zhu et al. A couple of years ago, they used the Fast Radio Telescope, as you said. They were surveying M94, just this lovely little galaxy. And I'm not sure the primary science behind it, but they were essentially imaging this galaxy at between about 1 and 1.4 gigahertz, more or less. And they have produced this beautiful map. Now, in the upper map, essentially you're looking on the x-axis at sort of longitude and at the y-axis latitude on the sky. Now, astronomers call these two axes right ascension and declination for interesting historical reasons to do with the fact that there's an offset between the right ascension declination plane and the longitude latitude plane on the Earth. But essentially what we think of longitude, latitude on Earth, when you project that into the sky, historically we've called that right ascension declination, and we can talk about that in another podcast. So essentially you're looking at a positional map here. And as Joseph rightly said, these contours, these color-coded contours, what they've done is they have transcribed or transposed, or perhaps the amount of radio emission they detect from they turn that into a quantity of molecular hydrogen that they observe in the universe and towards this galaxy based on the radio flux. And so the deeper the colors, as you can see toward the main blob of M94, Messier 94, there's just a lot more hydrogen there. And galaxies are associated with that because they have lots of hydrogen gas and they form stars and so on. And that's, a galaxy is basically a big bunch of stars with some gas and dust thrown in. And as you said, some of these satellite areas you can see, these 2, 3, 4, 5s up through 9, they're sort of blobs of hydrogen gas orbiting the main galaxy, which does occur. You see that we have several blobs of gas and stars orbiting the Milky Way galaxy. We have, in fact, I'm part of a project called DELVE, which detects dwarf galaxies orbiting the Milky Way, and we use that to study dark energy and probe the galactic gravitational potential. We have 2 nearby satellite galaxies, the Large and Small Magellanic Clouds, which are probably captured systems, but we would see these also in 21 centimeter line if somebody were observing the Milky Way from far away. And as you rightly said, one of these sort of hydrogen-rich blobs orbiting M94 caught the researchers' attention in this CLOUD-9, and it's Joseph has circled it right there. It is very, very dense. You can tell because the contours are very, very close together. There's very, very dense concentration of hydrogen, and it has some interesting properties that make it worthy of follow-up. And so, first of all, it's very, very large. There's an estimated several hundred million solar masses worth of hydrogen gas there. But then maybe if you want to tell the next part of the story, because I'm talking a lot. But we expect if you see that much gas material, you would expect perhaps some ongoing star formation, or at least evidence of star formation.
Yeah, and I just want to add too, something that might help the viewers build intuition for how this map works is it looks like a topographic map, it's because they're very similar. And whereas the contours in a topographic map represent lines of equal height, and then the density sort of tells you where peaks are, and the quantity you're interested in is elevation, like height above the surface. In a radio contour map is about brightness. And so just you can imagine this like a mountain of brightness. And so what we've seen here is a mountain of brightness from a galaxy that we know about, and then this weird, very high, sharp mountain of brightness on the side. And that's a CLOUD-9 and why it stands out.
Yeah, that's a really nice, I love that analogy. And that sort of mountain of brightness is actually saying there's a lot of hydrogen there, because that brightness and breadth is the 21 centimeter line blazing away, which means it has to be a lot of molecular hydrogen. But that's a really nice analogy. I like that.
So so one of the weird things about this blob was when we took a closer look at it was that first of all, it seems very cold. And so usually, like David mentioned, when you have a very big dense area of hydrogen, you get star formation and heats up. That's how galaxies are so visible. But when we looked at this thing, not only was it very cold, but it also didn't seem to have any stars in it. So you can measure the presence of this hydrogen. This is the observations from the VLA, which is that very big Y-shaped telescope. And you can measure the observations from the VLA that this hyperfine transitions, 21 centimeter line, and you can see there's an emission from hydrogen gas. But looking in the area, there's almost no visible stars. And this is really, really weird and really exciting. So, in the paper that came out more recently, the Anand et al. 2025, they took a much closer look at the area to see if there actually was secretly a galaxy there that's just hard to see, or if there was nothing. And they did a bunch of simulations to sort of visually place an upper limit on the mass of the galaxy that could be there. And they basically found that based on the amount of hydrogen that should be there, there should be a galaxy way big enough for us to see it very visibly.
A dwarf galaxy, probably.
A dwarf galaxy, yeah, but it should be big enough for us to see the presence of a bunch of stars from it and then the starlight from that. But we can't see anything. It doesn't look like there's anything there. So they placed an upper limit on how big a dwarf galaxy could be. And as David mentioned, the hydrogen gas is 10 to the 10 solar masses roughly. But if there is a galaxy there, it's less than 10 to the 3.5 solar masses. So tens of millions of solar masses of hydrogen, but the stellar mass of the galaxy that could be there, if there is one, is barely a couple thousand stars. So there's a huge mismatch between how much hydrogen we're seeing and how much stars there could be there. And remember, this is an upper bound. They're not saying they found stars there. They didn't find any stars in that region. They're saying that if there was, this is the largest number of stars that could be there, and we could detect it. So the way they did it is really interesting. They ran a bunch of simulations and then saw how many stars you could add before the number of visible stars exceeded the number of stars you could see in the area. And that's how they set the upper bound. And I can say a couple more things about what the physical implications are for the universe, but I don't know if there's anything you wanted to jump in and say there, David, before I talk about the cosmology stuff.
Yeah, well, before you jump into the cosmology stuff, and I'll sort of give the precursor to this, is first of all, it is very surprising. Now, there could be an age limit here because star formation does take time. But given the fact that this sort of blob of gas, especially with the fact that the hyperfine transition is sort of one in 100 million years, that's half, the sort of typical transition time is so long, we would expect this blob of gas to be of the order of billions of years. And the problem with that is, if there's no star formation, it's had so much time to have undergone some star formation. And as you showed in the previous image, it's quite cold. The velocity, by cold, we means the gas isn't very energetic. In fact, its velocity dispersion is about 10 kilometers a second, which is pretty low, and is certainly low enough that you might expect star formation to occur in that kind of velocity dispersion. One might expect it to have some induced star formation from M94 itself. And the other thing is, if it is hundreds of millions or more likely billions of years old, and this is where you're going to come in with your universal or your universe implications of gravity, it's somewhat strange that it's still a small, very condensed blob. Now, very small. I think the number I saw is it's something like 500,000 parsecs across. So it's quite large as things go galactically, but it's still a small, fairly compact blob of gas when we talk about galactic or universal or in the universe gravitational potential. So how did it stay in this small, compact blob of quite enriched, no, not enriched, dense hydrogen gas for such a long time? Why didn't it just disperse out into either become enlarged or just become part of sort of a halo of M94? That's a hard thing to explain as well.
The current explanation that the authors are trying to give from this, based on the paper, which I think a lot of people agree with, at least to the extent with the data that's available, is this is an example of a starless halo that is predicted by our current theory of cosmology. So cosmology deals with the timeline of the universe, like how it began, how it evolved, where it's ultimately going. And we have one theory that has made a lot of really good predictions called the lambda CDM model of the universe. And this is basically taking the universe as we know it with all this matter and stuff floating around, and it adds two components that explains the stuff that we haven't been able to explain yet. So one is dark energy. So we see the universe is accelerating. Lambda CDM incorporates dark energy via a cosmological constant, which is the lambda in the lambda CDM bit. That's an addition to Einstein's theory of relativity that gives a negative energy density to the vacuum of space-time itself, allowing it the ability to sort of expand. And that's for That's for the lambda portion. And then the CDM portion of lambda CDM is the addition of cold dark matter. So the idea here is you have a huge fraction of the universe, like 75% of all matter in the universe is this unknown dark matter. We don't know what it is, but we have some constraints on the properties, like it's cold, it's weakly interacting, and basically only interacts with other objects via gravity. We have some theories about what the cold dark matter could be, but lambda CDM does not try to place any constraints on that. However, the series already made some great predictions. Like, for example, it's predicted the power spectrum of the cosmic microwave background. So when the universe was cooling down, it was at first it was very, very hot because it was small and ton of energy, and all the radiation within it was just trapped and couldn't free flow because it was so hot. The mean free path of photons was very short and they couldn't escape to large distances. But at some point, the universe expanded enough and the temperature cooled down to the point where hydrogen could recombine into, the first protons and electrons could combine into hydrogen. And now photons aren't getting captured. They're just free flowing to infinity. This moment sort of, yeah.
The so-called epoch of recombination.
Right. And the epoch of recombination, and this leads to the cosmic microwave background, which is this imprint of all the emission in the universe 1 picosecond before the recombination, because all the photons that were getting absorbed and thrown around sort of free stream. And the cosmic microwave background has these very interesting blobs of energy on various scales. And the idea is that these were concentrations of or fluctuations in the universe that led to higher concentrations of matter and dark matter, which eventually spawned the first galaxies. And one of the predictions that lambda CDM makes is for the power spectrum of this. So if you take a Fourier transform of this image and ask what are the frequencies that blobs of various sizes appear, you get this graph of the multipole moments of the cosmic microwave background. And these data points are from our observations of the CMB, showing the frequency at which blobs appear. And so the lambda CDM makes precise predictions for what they should look like, which is the green curve. And it basically shows that it's basically in line with our predictions for the fraction of dark matter in the universe and dark energy and regular matter. The reason I say all this is because this is an incredibly specific and powerful prediction, and it's one of the most powerful predictions in astrophysics. But one of the things that lambda CDM predicts is that not every dark matter sort of halo will form a galaxy. So the conditions to make a big blob of matter are pretty easy. You just have some matter that starts to collect, usually dark matter, in these, or maybe across the cosmic web or from these quantum fluctuations in the CMB. And then eventually matter starts to fall in and you get a big blob of matter. Specific further conditions have to be met, like it has to be of a certain compact size, it has to radiatively cool very efficiently, and if those conditions are met, then the blob can collapse further and promote star formation, and thus we get galaxies. But we don't expect that to happen all the time. So we've been expecting that we should find big blobs of hydrogen that were concentrated around areas of dark matter that did not meet the conditions to produce stars. And these are expected starless halos, but we had never seen them before. They were an important prediction of lambda CDM, but we hadn't seen them before, partially because there's no stars, so they're very hard to see. We can't see them at any distance, basically. But even within the Milky Way's vicinity, we expect to see 5,000 of these objects, and we had it. This object, CLOUD-9, could be the first starless halo consistent with predictions from the lambda CDM model of the universe. And so that would be a really exciting new confirmation of that theory. So that's the sort of cosmological implications. I know I just talked a lot, but that's kind of the big picture overview.
I love that. I think you put that together really nicely. I could have said maybe 3 words of those 300 words you said.
That's for our listeners, that's not true.
No, that was actually a beautiful description. And
Thanks,
while
David.
you were talking, I was sort of listening to your dreamy voice, and it's like, oh my God, this guy is brilliant. It actually leads very nicely to a sort of more philosophical point, and we talked about this last week with one of the questions that Nora had asked us, is why do we do any of this at all? Why do we observe galaxies? Why do we look at the 21 centimeter line at 1.42 gigahertz? Why do we observe the sun? Like, who really cares? And I think you also put it really nicely last week, is that we talked about this when we talked about 3i Atlas, is that when you make, or you have ideas about certain things in the solar system, in the galaxy, in the universe, one of the most powerful things you can do as a scientist, apart from take observations, is then use those observations to make predictions. And one of the beautiful things about Lambda CDM is not only it obviously continues the work of Einstein very, very nicely, but it describes some of the observations we have made of the universe. It also makes predictions. And that's fundamental to science, because at that point, you're not just saying, oh, the moon is made of cheese. And everyone says, oh, great, with current observations, the moon does look like it's made of cheese. But then if you really do you believe that and you make that assertion, then you might want to make predictions that, hey, it might make a great omelet or a great cheese sandwich or in the universe.
We should see it change color with time as it cheeses.
It doesn't degrade in space. It's fine.
Good point. We have a cheese truther over here.
A cheese truther. But my point being is that when you do make physical observations of a system, it then allows you to make mathematical and scientific models to say, oh, well, if this is true and this model explains my observations, I predict this will happen. And what people like me and Joseph do, especially in astrophysics, but I think even with our lives, is we're pretty decent at saying, well, a certain set of conditions exist. We might expect this to happen in the future. And so the one thing I really like about the process you just described is Lambda CDM does make a prediction about what you should see. And so, starting with our Chinese colleagues, with Zhu et al., they went out and deliberately looked for those kinds of observations that were predicted. Now, Joseph and I do that in our respective sciences. In fact, we still do that with the Event Horizon Telescope. Joseph with a lot of his supernova work. I still do that with a lot of my DELVE work, my collaboration out of Fermilab there in Chicago. But this is even how I started my PhD, Joseph, is that I studied basically late type stars. And we did that because the sun itself is a late type object. It's a G2 dwarf. And we said, right, if we can observe something in the sun, we predict it should also happen in sun-like stars. And so we go and measure a whole bunch of sun-like stars of different ages, and the observations match more or less with what we were trying to figure out. But then we use those observations to try to predict or confirm the solar standard model, as in, do we understand how the sun itself works? And guess what? Turns out we didn't. So the standard model, for instance, for the sun predicts an awful lot of things about it. But one of the key components is missing. The solar model does not contain magnetic fields, and it does not contain rotation. Well, guess what? The sun rotates like everything in the universe, unless you prevent it from rotating, and the sun has magnetic fields. And so when you throw in the real physics to some of these predictions, we often can't always match our observations to those to the predictions from the models. Therefore, it shows your scientific models aren't correct. You have to go out and make new observations. Now, I sort of on my soapbox, maybe astronomically a little bit here, but that turns out to be really important, especially for, say, an object like the sun, because the sun affects humanity every single day, especially with these geomagnetic storms that we receive when the sun is in its peak of its activity cycle like we are now. But perhaps linking all this back to cosmology is one thing we cannot predict in the sun, and we can't even explain it well. We know why it happens, but we don't know why it's happened to such an extent, is of the three elements produced in the Big Bang, which are hydrogen, helium, and lithium, the sun's lithium looks to be a factor of about 100 lower than it should be based on Big Bang nucleosynthesis. Now, while we now know that lithium does get proton burned in the core and the hotter regions of the sun, above about 2.5 million Kelvin, we still can't explain the lithium content of the sun. And you're thinking, well, hang on, the sun's on our doorstep, it's really bright, we measure lots of photons for it, we've got an amazing suite of instruments to observe it, and we've got all these complicated models to explain it. We still can't explain it very well. Now, we do know there's convective mixing that's occurring way beyond what the solar model predicts, but that's of an object we can study really, really well. The kind of observations you've just talked about are actually very difficult to make, primarily because the objects are either very far away, very faint, or very small on the sky. And that makes observations of them difficult. Now, I loved your discussion of the Lambda CDM model because, again, it makes predictions that we can go out and test. And especially the podcast we did a couple of weeks ago for 3i Atlas, there are some, let's say, groups around the world that have said that this object is made of cheese, or it's made of something interesting that is with ideas that are somewhat not mainstream astronomy. And you mentioned this at the time on the podcast, they don't make predictions. And I think the mark of a good scientist is to say, I have some observations. I think I can explain them. And if that's true, I predict it will do this. And so,
I really love that, especially the tie back to kind of what really pushes science forward. And it's really hard to make predictions, but from a given theory. But that more so than anything, more so than having an experiment that generates data you expect, or more so than like having a hypothesis that turns out to be right. I think that in every sort of scientific revolution, it is the new theory that comes in, makes a bunch of truly novel predictions that end up being correct. Like Einstein's theory of relativity was exciting, and with Eddington in particular, with the Eddington experiment, it got a lot of attention because it predicted deviations of how much starlight would bend around the sun, and like that's great, and that got a lot. That was really exciting, but the reason Einstein's theory is still having this crazy impact 100 years later is because he predicted stuff, or people predicted stuff from the theory that nobody at the time could have even conceived of measuring, like gravitational waves and black holes. And that's where it's like it starts getting really rammed home as like, okay, this is possibly a legitimate view of the universe. And that's what lambda CDM does here. It's a very bold prediction to say everything in the universe we see is stars and galaxies, but I'm going to predict that a huge fraction of what's in the universe is actually these starless, lifeless husks that we've never seen before, but they're there. So, and it's exciting that worked out, and it's like a really strong motivation for the theory, which is in itself, to be honest, the part of the reason that this is so exciting, especially if you're a cosmologist, is the more lambda CEM turns out to be correct, the more problematic it gets because there are so many other issues and inconsistencies. And it's like it's not like the standard model of particle physics where it keeps getting proven correct to more and more decimal places, and it feels like this is as complete a description you can get of the universe without incorporating like gravity, basically. But with lambda CEM, cosmology is just so much. In terms of it's so much greener. Like there's stuff that really does not add up. There's nothing in the standard model as an equivalent to like dark energy or dark matter in terms of a big black box placeholder that we don't even understand at the most basic level. And so it's really exciting. It's like, all right, lambda CDM might be correct. And it has these huge unanswered questions that we can't just explain away with like modified Newtonian dynamics or maybe light gets tired on long scales. Like, so it's exciting. The more something like a theory like this gets proven correct, the more trouble you have sleeping at night. Like the Hubble tension. The Hubble tension is a great example, I think.
absolutely.
Yeah.
Well, yeah, again, just as you were talking there, so my mind was wandering a little bit to just the genius of Einstein in producing relativity and understanding the universe in that way, of sort of taking the next step from Newtonian gravity and physics. But his genius, I think his true genius, was actually the lambda part of lambda CDM was this
Mhm.
cosmological constant. And what he basically said in his field equations was, I'm going to add in this, I think it's actually, it's additive, but it's a negative sign. I'm going to
Mhm.
add in all of this stuff that I actually don't know about, because the universe could be doing strange stuff and I still don't really exactly know what's going on. So I'm just going to lump it into this cosmological constant, and it's a number, between 0 and 1. And he basically argued with himself for the rest of his career until he died in the mid 50s. He still said, "Well, it could be right, it could be wrong. I don't know. Is there stuff to prove it? I don't have the observations." And one thing I think was I think his genius was willing to admit, and you said this, that he lumped all the physics he didn't understand into this big black box, and he called it lambda. But he also then said, well, lambda might be able to change from place to place in the universe. And we're going to call that quintessence. And quintessence is basically a lambda that has a sort of a delta t or a delta xyz t function. It could change depending on where you are and when you are. And as you said, maybe photons get tired at long distances, which is a lovely analogy. I actually love that. And I think that's the real genius that both scientists don't always think about very often, and the science-loving public don't think about, is not just did he come up with this framework to understand the universe and the sort of really the bedrock of cosmology. He allowed that black box of, oh, I don't know a whole bunch of stuff, so I'm going to lump it in here, and hopefully people in the future will be able to figure out what that is. And you're right, I
There's
think we
a
still don't know what that is.
I think there's a funnier element to that story too. So this is the equation that David's referring to, which is the Einstein's equation. It's the relationship between the curvature of the universe and its stress energy tensor, which is derived from the Einstein-Hilbert action. And what Einstein sat down, and he had this. What David's talking about is Einstein sat down. He had this beautiful vision of the universe, where space tells matter space tells matter where to go, and matter tells space how to curve, and this beautiful matter energy equivalence. And it was all these basic postulates, and that gave him this equals this. And it was the most beautiful thing ever. And I was like, Einstein's a genius. It's perfect. And then Hubble comes along and says, actually, for no understandable reason, the universe is expanding. And Einstein was like, all right, we'll add this term to account for the expansion of the universe. He was very confident that this was just a dirty little trick, and that with more observations or a deeper understanding of the math, this would actually just cancel out and lambda would go to zero. And then it didn't. And then they got more observations and did more math, and it kept being not zero. And in fact, not only was it not zero, it was quite substantial. And this caused all sorts of other problems. Like, if this thing is real, why is the universe not erupting into flame all the time, everywhere at once? Caused a bunch of problems. And Einstein later wrote that the cosmological constant, just even introducing it so that people had something to explain it with, he called it the greatest blunder of it. What did he call it? The cosmological blunder or something like that? Because he was like, it was so inelegant and so ugly that he didn't even want to give people this ammunition to explain it using his beautiful equation. But it did. And to this day, this is still the limit of our understanding of this pretty much. And this happens a lot, like with Planck and the Planck's constant, where he had this beautiful idea, couldn't get the math to quite work out, so he added a little nuisance constant that turned out to be very, very, very essential, and try as he might, he could not get it to go away. And this is really why it's so easy to sit down and, like Aristotle, intuiting that men must have more teeth than women because their mouths are bigger. It's so easy to sit down and sort of logic yourself into a conclusion, but it is important to confront those conclusions with reality, because oftentimes there's something else there that's a real clue to that our understanding is not complete. And that is like the best part of being a scientist, I think.
Oh,
it's the most fun.
Well, you can tell we're already excited about it. And again, I have all these thoughts while you're talking, as you put it so elegantly. And I think you're right with Planck as well. And so I see the Planck constant, and I see the lambda, the little sort of inverted wigwam there, which is the capital letter lambda in the Greek alphabet.
You call it a wigwam?
Well, it looks a bit like a wigwam, yeah. Yeah, Native American wigwam. I used to love
those. Oh, gotcha.
Yeah, it just looked like a Native American wigwam. I used to love those. And I think one of the beautiful things, I think the way you just described it, is I see constants and sort of fudge factors like that as almost a clutch on the engine of observations to the sort of theory of how you drive the car.
Great analogy.
Yeah, sort of allowing you to sort of do the observations with how the theory works, and it really allows you that fudge factor to move backward and forward into alignment. And you're right, it's absolutely fundamental to how we understand science.
I love that analogy. Yeah, it requires the intuition and touch to just get the car going. You've got to feel what the friction point is. How much does it do our observations that we're just describing phenomenologically? How much of it is theory that we feel really good about and confident about? And where is that interface? And how wide is it? How narrow? I love that. I'm gonna steal that. When you said clutch originally, I thought you were misspeaking and you meant to say clutch, but clutch is even better. Like that's genius.
Yeah, I was really hoping that it's how really you engage the theory with the observations, and how malleable you have to be with the clutch point as how the observations fit. Because, in fact, it brings me back to what we did last week, and I love that we're tying in our previous podcast. Was it last week or the week before? I think it was last week. Oh, no,
Atlas was 2 weeks ago, yeah.
2 weeks ago. And I think we did a good job at the time, and I think I did misspeak on the spectrum there with the and it was with the dust continuum profile down at near 1 micron or 1.234 microns. I was sort of implicating it was the sort of observations themselves and how the telescope had observed the data. Well, one thing we have to remember is all astronomers, of astrophysicists, when they deal with data from different telescopes, and I was just thinking about this for this podcast, is how do you compare data from the FAST telescope to the VLA system in New Mexico to the Green Bank telescope in West Virginia? And what a lot of astronomers do, and we do this with the Event Horizon Telescope for all the telescopes we have around the world, is we do something called data reduction. A data reduction is typically, it was called data reduction because you typically started with a vast volume of data and it reduced in size until you produced an image or a spectrum. But what you have to do is you have to take out the observation signature, basically the telescope component. And so you do that by taking away things like the instrumental effects and the atmospheric effects and the filter effects and the exposure time and so on. And so when you and I were discussing the dust component of the emission from 3A Atlas, all of that telescope signature, the so-called the instrumental signature, the instrumental profile, had already been removed. And so in fact, what we were actually looking at was the thermal dust emission. And it was in fact based on the quantity of dust and the temperature of the absorbing radiation from the sun. And I think we talked ourselves to the correct answer, but I think initially I went down the wrong path of, oh, it could be for the telescope or this. It's like, no, hang on. They must have done the data reduction such that the instrumental profile has been removed.
Yeah, I remember we took a look, and they had both. They had they had the one with the black body spectrum, and then
Yes.
yeah. And for sure, I think it would be malpractice to post a spectrum that has instrumental it doesn't have this instrument spectra a sensitivity curve subtracted
People
out
do.
and stuff like that.
People do. I've seen it in papers I've refereed. I'm sure you have too. Is that
I've never seen that. That's
oh, I have.
crazy.
Oh, I have. So yeah, a referee process, by the way, for our three listeners is when you receive a scientific paper where you submit it to the journals, they send it out to an expert in the field, and they review the paper for things like that, inconsistencies or poor data reduction techniques, or are they making sensible inferences from models and observations. Well, Joseph and I and all scientists, we have to, not only do we submit our scientific papers to the journals, we also review other people's, because that's part of the honesty and the peer review process. And one of the first questions you ask in observation-based papers is, did you remove the instrumental profile of your data? And so when you were showing some of those images there from the FAST telescope in China and the VLA down in New Mexico, the Green Bank telescope in West Virginia, is they have the instrumental signature removed. So it actually doesn't matter which telescope was used, you don't see that profile imprinted on your data. And that's how you know you get to the true observations. And that really is what drives the models that we were talking about.
And gives us confidence in their validity and veracity.
Yeah, absolutely. Yeah, absolutely. And that's a big part of what Joseph and I do in our research. Actually, the very first thing you have to do is get it onto a system that anybody could take around the world with any instrument, any telescope.
Reproducibility is the key.
Yeah, well, that's a big part of it. Reproducibility is huge, of course. And you know, you saw that in some of the greatest scandals in science, where the cold fusion team, yes, nobody was able to reproduce the cold fusion. And then also, was it out in?
It was Jan Hendrik Schoen for the superconducting organic superconductors.
Yeah, and
Yeah.
who I can't remember the guy's name now, but I think it was either out in Berkeley or I can't remember where, but with the 118 atomic mass, the atomic mass island.
Yes, yeah, I remember that. That's crazy.
They created, and basically the data could not be reproduced, and it was because only one person had written the code
Yeah.
to look at the collision data from the accelerator, and they said, oh, only one person in the world can reproduce a mass island of 118 protons in the nucleus, and it turned out that he was fudging the code.
Mhm.
So you're right, reproducibility in science is so important, and it's one of those things where. Like I said, I think we talked about this on a previous podcast, is I observed Tau Boo B in 99, and we published the paper in 99 of how we detected the reflected starlight from the planet orbiting Tau Boo. And we had the 2.7 sigma detection, which is decent, but not perfect, as we discussed last week in terms of statistical significance. And our nature referees, one of the nature referees argued with us about whether it was statistically significant. And we swore up and down how we'd been careful, and we had been careful. And we went and observed it again the next year with the same technique and the same instruments and so on, and we couldn't reproduce the signature from the planet.
Well, I think that's a really important thing that I think needs to be talked about more, which is even if science is done completely perfectly, all statistics are handled absolutely perfectly, you will still get flukes a huge fraction of the time, which is why reproducibility is something that cannot be replaced or sidestepped. And that's a really, really important thing that I feel like strongly gets overlooked. even if science is functioning properly, because wrong hypotheses outnumber real hypotheses or correct hypotheses by such a large number, even if everything's working as it should, 50% of the scientific literature that's sort of experiment based is expected to be incorrect if not reproduced. And so that's like there's a really great Veritasium video about that. And it was eye opening from a statistics perspective. But that's like something I found really interesting. And one thing that I've learned from the astrophysics side of things too is we operate in a really problematic regime because we often observe one-time transient events that cannot be reproduced. And so there is a very, very high standard for observation fidelity in astrophysics. I have received advice that, like, if you're designing a theory, like, most theories are wrong. And so it's like, okay, if your theory is not right, as long as it's sound. But if you are submitting an observation, it has to be right 100% of the time and 100% of the way through, no ambiguity. And David gave an example here where, like, he was, you were in a situation where your observation was right all the way through and your statistics were perfect and everything was double and triple checked, and it still ended up being a fluke, which is why it is so extra important that we are not being sloppy, because that just dramatically increases the rate of problems and that sort of thing. I'm very fascinated. I know we're getting a little off topic. We should probably bring it to a close on CLOUD-9, but I'm very interested in this whole topic, and you'll probably hear both me and David bring this up a lot in the future because I think it's something we're both interested in.
Yeah, well, it's the excitement of being a scientist, and it's that obligation to be honest. And when you don't think you've either got enough data or the observations aren't good enough, you're honest enough to say, if I saw this if I was refereeing this paper, I myself wouldn't believe it.
Yeah.
And sometimes we've both been in this position where you have a cool project and you've put together, a series of observations or models, and you know for a fact that it's on the board, it's on the edge, it's on the border of being rigorous. Not that it's wrong or that you've cheated, you just don't have enough data to support the model, or the model doesn't quite fit, or something like that. You have to be scientifically honest to say, I can't publish this. It's just not good enough.
Well, I mean, so this is coming from a real story, but I actually just had not necessarily you can't publish it. You have to be very, very upfront about the level of if your analysis not relying on these potentially unrigorous points. We just published a paper last year that had a very, very intriguing data point that was only a 2 sigma detection. And then even after a lot of very careful handling of statistics, we were only able to improve the significance to 2.7 sigma. And it would have been really cool to go out and make this statement that, oh, we have the earliest data point on this thing and blah, blah, blah. But instead what we did was we said, we actually don't know if this is real or not. It's only 2.7 sigma, which is like almost good enough. Like, it's almost at that rigor threshold. But so at the end of the day, we published, like, in the paper, we have 2 separate versions of the analysis, one with the data point and one without it. And they gave the same results. And we said, in our opinion, we think the data point is real, but here's the full story for you to decide. And so certainly, if your analysis is on the edge of, like this, you don't have to scrap it if it's not good. But I think what the point David was making, which I strongly agree with and want to echo, is the honesty. It's like, just don't. There's nothing to hide. There's nothing to. You just show what you got and be honest about it.
Yeah. Well, I don't know if you remember this when we were the early days of doing the imaging analysis for the Event Horizon Telescope project for the imaging the black hole, and this was when you and I had first met, actually in 2018, and you were an undergrad research intern, and you and I were in the first days of knowing each other and being silly. It was, you probably remember, I was a little bit hard on the imaging team because I would say things like, can you still reproduce this image of the black hole if you, say, remove 10% of the data? Or if you randomize 10% of the data, do you still get the same result? Or if I give you, I think we have 4 imaging teams. If I give team 1 80% of the data, team 2 78% of the data, team 3 90% of the data, do you still get the same answer?
Well, this was, and I was on the imaging teams, and I remember you and others bringing up these concerns. And what ended up happening was we didn't just run the tests or ignore them. We ended up, that was a key part of the analysis, was we had a whole suite of appendices with exactly these kinds of tests, and we showed exactly where the image structure breaks down and how much data is needed and where the flaws sort of lie.
Yeah, no, I remember that was super cool. And again, that's that rigor which is why the 2019 image is still so robust, is because we ran ourselves through the ringer of being meticulously honest about the data quality, but also then doing these blind imaging surveys, if you remember, to say, okay, team one, you do an image reconstruction, but we're not going to give you, we're going to give you a certain set of parameters, and we're not going to tell team two about those. So you all worked independently. And when all four teams produce more or less the same image, it's like, oh,
That
okay.
was the big. That was exciting.
That was pretty exciting.
I mean, I think that was the really big moment. Even though everyone was internally excited when they imaged within their own teams, they got a ring. It was the moment we put it on the projector, and all four teams saw all four images for the first time, and we're like, "Oh my god, that was so cool! What a great memory!"
Yeah, no, it really was. And but that was the scientific method for me, is that we were our own worst critics. And of course, before, and if you probably remember this, but before those papers were released, we went over them with a fine-tooth comb, and we had different teams go over the papers and look for flaws and do the double, triple checking of the data reduction and the phases of all the telescopes and checking their, their X, Y, Z positions on the Earth, everything, because we obviously, for such a big result, you should do it for every result, but for such a groundbreaking result that would basically sort of reinforce Einstein's theory of relativity, 100 years later, we wanted to be extremely rigorous. And any question the referees could come up with, we
wanted to have thought of first.
Yeah, I think we wanted to be self-critical and sort of, again, that sort of scientific honesty. It's I mean, as you say, we're way off topic, but it's just so fundamental to what we do professionally.
I agree. I think we could probably bring it to a close now. CLOUD-9, super exciting discovery, big implications for cosmology. David, thanks for providing all the insight on the telescopes and the background of the observations. I'm looking forward to seeing more groups sort of validate this, because unlike a lot of transient events, this is something that can be repeatedly done and explored in more detail and we can point big. So there's going to be expect to see a lot of stuff on CLOUD-9 coming forward, and hopefully more of these objects being discovered. But until then, David, thanks for being with us today.
Thank you, my friend. Thank you for such an elegant Lambda CDM discussion, and as always, thank you for your elegance and your hosting prowess.
Thanks, David, and thank you to our audience for listening. We'll see you next week.
Take care.
Love you, man. Bye.
Love you too, brother. Bye. Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.